Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey everyone, hope you all had a wonderful holiday. Over the next few weeks, we'll be running back the clock with our second annual AI Rewind series. Joined by a few friends of the show, we'll be reviewing the papers, tools, use cases, and other developments that made a splash in 2019 in key fields like machine learning, deep learning, NLP, computer vision, reinforcement learning, and ethical AI. Be sure to follow along with the series at twimlai.com/rewind19. As always, we'd love to hear your thoughts on this series, including anything we might have missed. Send me your feedback or favorite papers via Twitter, where I'm at Sam Charrington, or via a comment on the show notes page you can find at twimlai.com. Happy New Year. Let's get into the show. All right, everyone, I am on the line with Chelsea Finn. Chelsea is an assistant professor of computer science at Stanford University. Chelsea, welcome back to the TWIML AI podcast.
Thank you, Sam.
All right, so we have not spoken since it's been quite a while. You were at Berkeley at the time. It was back in June of 2017 for TWIML Talk number 29. We're over 300 shows now, so quite a while. Before we jump into our focus for this conversation, which is a look back at 2019 and all the exciting developments in reinforcement learning, why don't you catch us up on what you've been up to over the past couple of years?
Yeah, so I finished my dissertation at UC Berkeley. Now I'm an assistant professor at Stanford. And I guess in my research, some of the things I've been really thinking about recently are how we can build machine learning systems, and especially embodied systems such as robots, that can generalize to different objects, to different environments, to different settings. And this is through the lens of reinforcement learning algorithms, as well as what's called metalearning algorithms, where you try to accumulate previous experience in a way that allows you to quickly learn new things or quickly adapt to new settings, rather than trying to learn from scratch for every new thing that you might want to do. Mm-hmm. So my group at Stanford has been starting to study some of these problems in generalization and reinforcement learning and robotics. And excited to be on the show today.
Nice. And you're also teaching a course at Stanford now on metalearning. Is that right?
Yeah, absolutely. I'm teaching a new course that is just wrapping up. We have our last class on Monday of next week. And then after the course, all of the videos are going to be available online for the public to see. All the videos of the lectures.
Oh, that's fantastic. That is fantastic. So the format of this particular conversation is going to be, again, focused on 2019 in review and reinforcement learning. Before we jump into the specific papers or topics that you thought were interesting this year, can you kind of characterize the year for us, relative to other years that you've been following RL? How was 2019 shaped up?
Yeah, I think that research in reinforcement learning has really been picking up, and there have been an increasing interest in it. So there are more labs that were traditionally focusing on supervised learning or unsupervised learning that are now going into this setting where agents need to make multiple decisions, and people have different motivations for doing that. But I think that really the field is expanding, and that's been an exciting time. And also with that expansion, I think that people have been studying a broader range of reinforcement learning problems. So before, people were kind of narrowly focused on a few benchmarks, and I think that now that is opening up, and people are kind of reconsidering different formulations and different problem settings within the context of reinforcement learning. And with that, there's also been some of the same big players that have been trying to advance the capabilities of our reinforcement learning systems as well. So I think that there's been progress on a lot of fronts, and it's been a pretty exciting year.
Now, the benchmarks that have traditionally been used in RL, at least the ones that come to mind most immediately for me, are video games. And in particular, historically, it's been kind of simple Atari-style video games, but these have been getting a lot more complex over time.
Yeah, absolutely. So one of the big focuses in reinforcement learning has been looking at Atari games, and there still actually were some really interesting progress made on those benchmarks. But I think that also a lot of research has been opening up and focusing on other problems as well. Another very common benchmark in previous years has been these continuous control tasks of these simulated robots in the Majoko physics engine,
Hmm.
and using
This
like
is
OpenAI Gym, for example.
an
And
example of
those
that
help.
would be like the cart pole.
Things like cartpole, but also what's called the half cheetah or the ant, which is actually a four-legged creature. These types of simulated locomotion tasks.
Ah, okay. And so we'll see these videos with, an agent essentially learning to walk or trying to get from one place to another most efficiently. Those types
Yeah,
of benchmarks.
exactly.
Got it. Okay. All right. Awesome. So, your task in preparing for this session is to come up with a few, or was to come up with a few papers that you thought were significant. You, in fact, came up with topics, some of which had multiple papers that you thought were really interesting. Why don't we just jump in and have you walk us through these?
Yeah, so I think that there's often never just one single paper that really solidifies and a result. There's often many multiple results that actually really show you what is capable and what you can what these algorithms are capable of and what can be done with our current technology. And so that's why I wanted to focus on these different topics because I think that there are it's not just one paper for each thing. So the first thing that I wanted to highlight was thinking about reinforcement learning in the real world. So there's been some pretty impressive progress on reinforcement learning on real robots for dexterous manipulation tasks. So think like a five-fingered hand that can do things such as turn Rubik's Cube sides, or can manipulate two what's called bouting balls in the palm of the hand and rotate them with a single hand. And so we've seen reinforcement learning algorithms that are able to learn both of these very dexterous manipulation tasks with five-finger hands in the real world. So but one of the things that was interesting, there was actually two papers that showed these results. One that actually trained completely in simulation and then tried to transfer what was learned in simulation to the real robot, and one which learned completely in the real world and was actually efficient enough to run in the real world. And so one of the things that I found really exciting about these results is it showed the sort of complexity that we could learn in the real world using reinforcement learning algorithms. And it was interesting to see how divergent the two approaches were for accomplishing somewhat similar objectives.
How would you characterize the divergent nature of these two approaches? What were the key things that they did differently?
Yeah, so the key thing was simulation versus real. So one
Okay.
of them
Okay.
was, and it's I guess a little bit more of that. One of them was trying to take a really powerful reinforcement learning method and train it in a variety of different simulated settings in a way that allowed it to transfer to the real world. And one was extremely focused on efficiency. So if you're running on a real robot, a five-fingered hand that is a bit fragile, it isn't something that you can really put a lot of wear and tear on. Then you need to be extremely efficient. You need to be learning in a way that you don't break the hand in the process of reinforcement learning. So the kind of two algorithms that were developed here were, in many ways, just like completely different from each other, but yet achieved a kind of similar result in the real world.
And the Rubik's Cube paper, that's a relatively recent one in the year, and that was some results by OpenAI, and those caused a bit of a stir in the community that the results they presented were overhyped or overmarketed. Do you have a take on that?
Yeah. So I think that the concern was that the kind of the title of the approach or of the blog post was about solving Rubik's cubes using reinforcement learning, and what they were actually doing was they were using a Rubik's cube solver and then figuring out how you could do they were using a Rubik's cube solver to figure out which face to turn in which way, and so that kind of was in some ways pre-specified, and then the reinforcement learning part was figuring out how you can turn that face with a physical hand.
Mm-hmm.
And so this was a bit controversial because it was people got the impression that they were learning all of the moves of solving the cube with reinforcement learning and not just the physical aspect of it. In many ways, I actually think that the physical aspect of it, while it seems like it should be simpler because we are like basic manipulation skills are so intuitive and basic to us, I think that actually in reality, this sort of physical contact is actually much harder than solving the Rubik's Cube. We've had solvers for Rubik's Cubes for a very long time.
Right.
This is one of the first times that we've actually seen a robotic hand be able to have the dexterity that allows it to rotate one of the faces.
Well, and there are so many more degrees of freedom with the hand than the cube itself.
Yeah. And so, yeah, there was some controversy there, and also just generally the way that things were handled with like the press and everything, because they also put a significant effort into producing a video and like marketing the work. Whereas in contrast, a lot of research labs don't do that, as you might expect. So there was also some controversy there.
For the record, we'll include links to all of these papers in the show notes. The ones we just spoke about were Solving Rubik's Cube with a Robot Hand and Deep Dynamics for Learning Dexterous Manipulation.
Yeah, and the second paper was by Anusha Nagabandi, who is a PhD student at UC Berkeley and was doing an internship at Google Brain at the time.
Okay. Great. So lots of progress on applying reinforcement learning to manipulating physical objects with robotic hands.
So the second approach that we talked about that by Anusha was using a technique called model-based reinforcement learning, where you learn a dynamics model of the world and then you do reinforcement learning using that dynamics model to optimize a policy or to optimize over actions. And so this kind of approach in general, I think, has in some ways received less attention by the machine learning community than model-free reinforcement learning methods. But this year, I think that we actually saw an increased interest in model-based reinforcement learning methods. And one of the reasons why people do like to use them is they tend to be more sample efficient. But the challenge is if you're in a vision-based domain, if you only see images, if you only see image pixels as your observations, then in principle, learning a model involves potentially even predicting pixels forward into the future, like learning a video prediction model, and that can be very challenging.
Mm-hmm.
And so this year we saw some real progress, I think, on model-based reinforcement learning on vision-based domains. One approach that predict pixels into the future. So I was actually learning a video prediction model and showed how you could use this for things like Atari games. And one which bypassed the need to predict pixels by predicting forward in a latent representation learned by a neural network and using that latent representation to predict things like the future values and the actions of a policy. And so I guess one of the things that I was really impressed by and thought was interesting with these two works is that it really showed the viability of model-based reinforcement learning as an approach, even for some of the benchmarks that have been so heavily studied by model-free approaches. So I think that there are a number of benefits of model-based, and I wasn't necessarily thinking that those benefits would come on things like Atari, for example, but we were able to see significant progress from these works on those domains.
In the case of the Atari work, what does a model look like in that context?
Yeah, so for the first paper, the model was actually generating images into the future. So it's a big neural network. It's fully convolutional. So it's basically taking in an input frame, it produces convolutional feature maps and produces a representation, and then has deconvolutions to produce the next image and it also takes as input the action to produce the next image. So it's trying to predict what will the next image or the next sequence of images look like given the current image and a sequence of actions.
And then that future predicted image becomes additional input to the RL learner?
So yeah, so then that image you can use to essentially generate more data for your reinforcement learner. So instead of always taking actions in the real environment, you could also take actions in this learned environment and use that to improve your policy.
Sometimes when we use model-based approaches, the model isn't necessarily a learned model. Is it a learned model in both of these cases?
Yeah, so in both of these cases, it is a learned model. There's a field, especially prominent in robotics, called model-based control that typically assumes that you know the model of the environment. And I guess it's not just in robotics as well. There are a number of approaches where it assumes that you know the model, you know the kind of the true simulation of your system, right, and you use that known simulation in order to learn the task. And in many ways, in Atari, it's a little bit, in some ways, a little bit silly to actually learn the model because you actually have the real simulation system. But I think that in many ways, the reason why people care about these approaches that actually learn the model is that it means that it's applicable in settings such as the real world, where you don't know the model.
And so in both of these cases is the approach essentially the same where you're using model to predict images into the future?
So the first one is predicting images into the future, and the second one is actually predicting other quantities into the future. So it's predicting things like values, rewards, and actions into the future. And this is all of these predictions are conditioned on some latent representation. So you can think of it as predicting only the quantities that are relevant for the game, but in some latent representation, rather than having to predict all of the pixels, which include things that aren't necessarily relevant to doing well on the game.
Got it. And so the pixels that you're predicting here might be pixels that represent things on the screen that are specific to actions that might be taken, like, I don't know, a score or some kind of trying to come up with a good example of what that might be, but specific symbols on the screen, or are we is the model predicting out of pixel space?
Yeah, so in the second one, it's not actually predicting at all in the pixel space. It's basically has a neural network that takes as input the image and produces a vector, a representation, and then it predicts that representation forward rather than predicting the pixels.
But the fundamental, in both of these cases, we're starting from vision and pixels and using that to using models based on these pixels to kind of inform an RL learner, an RL agent.
Yeah.
Okay. All right. And so the next category that you wanted to cover is focused on batch off policy RL. What is that?
Yeah. So, and actually the next two topics are focusing really on generalization in reinforcement learning in a way. So what batch off policy RL is say that you have, so I guess let's first talk about kind of the standard reinforcement learning setting. So in the standard reinforcement learning setting, your agent collects some data, you learn from that data, then you collect some more data, you learn from that data, and you iterate this process. And what off-policy reinforcement learning methods are methods that, I guess maybe I'll start with on-policy methods. On-policy methods, they collect data, learn from that data, and then they throw away that data and collect a new batch of data and learn. And so they're always collecting data from their current policy, their current actor, and they don't have a way to reuse any data that they collected previously because they need the data to be from their current policy. Now, off-policy methods are ones that can actually leverage data that they collected from previous policies. They're ones that can leverage what's called off-policy data, data that's not from your current policy, your current behavior. And these algorithms tend to be a lot more efficient because you're not throwing away data at every single iteration of your algorithm. Now, batch off policy RL algorithms take this to an extreme where they assume that you actually are just given a batch of data from some policy according to some behavior, and then try to learn from that, and they don't have any ability to collect more data in that environment. And the reason why this is really important and interesting is that, first, if you think of just the majority of machine learning, you consider, like, you often have settings where you have some data set, maybe something like ImageNet. You're just given a batch of data and you want to learn from that data. And if we have algorithms that can just learn behaviors and learn policies from a batch of data, that means that we can start just accumulating very large and diverse data sets and allowing algorithms to learn from them without having to kind of have this iterative data collection process in the loop. And the second reason why it's important is that if there are a number of settings where it's unsafe or not possible to collect more data, such as if you imagine, for example, wanting to learn how to make medical decisions, you want to learn from data of doctors' decisions, or maybe you have another system that's interacting with users in a way that isn't safe to take actions in random ways, then you want to just be able to use data from doctors, for example, and learn from that data without having to experiment or collect more data by kind of randomly taking actions or by exploring. Does that make sense?
It does. One question I have is, does the sequence of actions, is that necessarily included from or excluded from the typical problem setup for batch off policy RL?
Yeah, so typically you do assume that you have the actions that were taken as well. So you know, like, what action or what decision the doctor made in the medical decision-making example.
Mm-hmm.
But one quite interesting setting would be maybe you have some data with actions, but some data without actions, like you're just observing humans on the internet doing stuff. And maybe you could try to learn how to manipulate objects from that data. And that's a setting that some students in my lab have actually been studying recently.
Oh, interesting. Yeah, that question was prompted by your idea that, at some point we might just be able to take some collection of data and learn from it using a off-policy RL agent. But that would seem to assume that there's some known sequence of actions that you'd have to have that. And that seems to make it less of a natural data set, if that makes any sense. With that background in mind, what were the specific advancements in the couple of papers you identified on this topic?
Yeah, so I guess getting back to benchmarks, we actually don't have really good benchmarks for this setting that actually have meaningful real-world settings. But the algorithms themselves showed a lot of promise towards enabling good learning in these settings. So the first one actually took the replay buffer of an agent on Atari. And when they only took this replay buffer, they were actually able to outperform the policy in that replay buffer just by learning from that data. And so that result, I think, was quite impressive, and also is just a suggestion that we should be able to learn very well from these types of data if we set up our algorithms well. And then the second approach, which actually the second paper that I linked, which actually predates the first one, also showed quite strong results. They weren't looking at the Atari domain. They were looking more at these continuous control domains, but they also showed the ability to learn behavior from these kind of batches of data. Not quite to the extent of the replay buffer, if I remember correctly, but we're showing pretty strong results there.
The paper that's looking at the replay buffer, the result seems counterintuitive. If I'm interpreting it correctly, you basically have this replay data from a RL agent. So everything the agent kind of saw as it was exploring these games, and then you give it to another agent to learn off of, and the agent somehow performs better than the original agent, but it doesn't see necessarily anything more than the original agent saw. Is it that it has access to all of it at the same time, whereas the original agent only saw it in snapshots?
So yeah, that's a good point. I think that the reason is that they didn't train the first agent completely to convergence. They just took they took a batch of the kind of the log data from that agent before it had reached its max performance, and then showed that and there was some room for improvement. And if you would give the online agent, I think, more data, it would have achieved the kind of maximum performance, or would have achieved at least as well as the offline agent. It was just that they kind of stopped things early and then wanted to test, can you do better with this batch of data? This gets to the question of how should we set up these kind of the experiments with batch off policy reinforcement learning methods. I think that things like training on logged DQN data or logged data from Atari isn't a great experimental setup, because it doesn't necessarily test the types of things that we want from these algorithms necessarily, because we may not have that sort of data when we're learning, when we're performing reinforcement learning in real world settings. But it still, I think, is a step in the right direction, and at least people are starting to study these kinds of problem settings
and proposing benchmarks for them.
Yeah. So I guess one of the reasons why I found it interesting wasn't just the kind of the results, but also the visualizations and some of I think it provided an understanding of the problem in terms of understanding what we can do in these problem settings to do better, and basically what are the kind of sorts of things that we might try to do, and in terms of solving this problem. So when you move from this kind of batch setting to a policy that you're learning from that batch of data, you have this distribution mismatch between the states and actions visited by the first policy in that batch of data and the states and actions visited by the policy that you're learning, the behavior that you're learning. Mm-hmm. And so it provides some nice visualizations into understanding how we might try to handle this distribution mismatch. And in particular, they focused on the action setting, the distribution mismatch in the actions, and made some nice visualizations for understanding what is actually happening under this distribution mismatch.
And this distribution mismatch is what they're calling the bootstrapping error?
I believe so, yes.
Got it. You mentioned that this work on batch off policy, as well as the next paper that you had in mind, RL with diverse offline data sets, are kind of common in that they're both tackling generalization for RL. That can mean a lot of things. In what sense are these focused on generalization?
Yeah, so I guess the papers that we just talked about, they actually aren't really focused on generalization, but I think that if we build better batch off policy reinforcement learning methods, we'll have the ability to learn from more diverse data sets because we won't be collecting data for every, within the context of our algorithm. So, for example, in the context of robotics, say, if you want to generalize to something at the level of ImageNet, that would mean that you'd have to collect an ImageNet diverse size data set in the context of your reinforcement learning experiment. And that just isn't practical, right? So we need to think about how we can have algorithms accumulate data into a large data set and then actually start sharing data, just like the rest of machine learning does. So if we can build these very large data sets by having robots collect data and then store that into a very large buffer of data and then have algorithms that can learn from that very large buffer of data without having to kind of recollect it in the loop of reinforcement learning, then we can start to see the generalization that we see in supervised learning settings. So this next paper is actually trying to start to study that. Like, can we build a very large and diverse data set and then learn from it?
Is it too far of a stretch to say that this is kind of pointing us in the direction of a kind of a transfer learning type of approach as applied to RL?
That's a good question. So in this particular paper, it is in many ways pointing at a transfer learning setting where you learn from this data set and then you learn representations for control, and then you take that representation and then try to transfer that to a new setting. It's analogous to ImageNet pre-training, for example. Like ImageNet, you can pre-train on the ImageNet data set and then fine-tune your features to a new task that allows you to transfer all of the rich diversity from ImageNet to your new problem setting. And we did something similar in this paper where we collected a very large data set, learned on it, and then transferred to new robots, transferred to new experimental setups. Mm-hmm. But so I think that it potentially points towards that, but I also think that we may be able to ideally be able to not just study transfer learning and also be able to just generalize in zero shot to new domains and new problems.
And so this paper that we're talking about is RoboNet Large-Scale Multi-Robot Learning. If I remember correctly, you did some work in grad school at Google Brain on a kind of a large-scale parallel robot platform. Is this similar?
Right. So the work back at Google in 2017 or like 2016, 2017, it was actually parallelizing across 10 robots at Google, but they were all the same robot platform in the same environment. And so if we care about, so it was really an important step towards this work here, but it wasn't, and in many ways served as the foundation for the work that we're doing in this paper in RoboNet. The key question that we're trying to answer now is, if we don't have 10 robots, like which most labs don't, my lab at Stanford does not have 10 robots, can we share data across institutions in a way that allows us to get the diversity of having multiple robots, of having many robots? And if we can think about having institutions and universities share data across robots and across labs and across experimental setups, then we can get away from having each individual lab to have to collect their own like ImageNet size thing.
What is the nature of the data that we're talking about sharing? Is this image data? Is it some other type of data?
Yeah, so in this paper, the data corresponded to trajectories of images and the actions the robot took. So it's essentially video plus a sequence of actions that corresponded to that video, to that outcome of images.
And is it video kind of off robot video or video from the perspective of a manipulator or something else?
Yeah, so we actually included multiple camera viewpoints in the data set, such that some of them were somewhat of a first-person perspective, some of them were more of a third-person perspective, really corresponding to just different camera placements around the robot. And the total number of viewpoints we had in the data set was actually over 100.
Okay.
And the data set also included data not just from so in the Google data set, it was like 10 robots, one robot platform. In this data set, it's around 10 robots, but it's like 7 robot platforms. So a significant diversity in actually the kinds of robots and the colors of the robots and the kinematics of the robots across these different labs and across 4 different institutions.
Okay, and the specific learning objective in this setup is what?
Right. So this is where batch off policy reinforcement learning methods come in. So if you have all this data, you need to figure out how to learn from it.
Mm-hmm.
And then, the good question is like, what is the reward function, right?
Mm-hmm.
What should you learn from this sort of data? In this particular setting, we actually use model-based reinforcement learning methods. So we were learning to predict video based off of the actions that the robot took. And then once we had this model of the world, then we would actually use that model at test time to accomplish different tasks. So we would give it a new task at test time, and then it would use its model to plan to achieve that task using its learned model, rather than trying to learn a policy during training. So it actually is kind of learning behavior on the fly at test time using its learned model. And then the kinds of tasks that we were testing on correspond to like manipulation tasks, like picking up a cup and positioning it next to other cups, or pushing a pencil to be next to some other pencils.
Okay, so in the case of a cup, you've got a model that you've learned off of the data set offline that has basically kind of built out a view of the world. If I do take some action on the cup, the future world is probably going to look like this. And then you then give a live robot access to this, and it's also being trained in a RL. Is it also an RL agent that's training that when it's live, or is it some other kind of approach?
It's not quite reinforcement learning. It's more just in some ways like model-based control in some ways, as we were talking about before, but with the learned model. So it's what's called planning. So if you have a model, if you know if you have an understanding of what will happen if you take some actions,
Mm-hmm.
then you can use that model to plan a sequence of actions for trying to accomplish a goal. So
more like an optimization problem across the likely outcomes from the model that you already have.
Yeah, exactly. It's this optimization problem over actions given a goal and your model.
Mm-hmm. Okay.
But one of the things that we're doing next is we're trying to look into if we can annotate rewards in the context of in this data set for different tasks, and then that would allow us to try to do some of this training, do some of this optimization over policies, over behaviors at training time, so that we could study algorithms like model-free methods.
And annotating a reward in this context means that if the goal is to stack cups, that the cup is, a picture where the cup is stacked, or are we talking about something more elaborate than that?
Yeah, it could be something like that. And it may, one of the things that's a little bit challenging in robotics context is that if you have a picture of cups that are stacked, that doesn't mean that you actually have a good reward function for that. So it's actually hard to compare two images. Like if you have an image of cup stacked, how do you know that another image also has cup stacked or also is achieving that goal in some way?
Mm-hmm.
So one of the things we'd be thinking about is just really simple things like label if an object is being grasped by the robot, like 1 if it's being grasped and 0 otherwise, and then we could use that reward function for grasping to learn a policy for grasping. So we're thinking about very simple reward functions like that, like are there cups stacked in this image, or is the robot holding something, things like that.
All right, so then the next couple of papers that you called out are focused on the broad curriculum learning area. What's been going on there? If I remember correctly, we talked briefly about that a couple of years ago in that podcast we did.
There were 2 curriculum-based approaches that I found to be quite interesting and exciting this year. And in both of the cases, the agent was actually coming up with its own curriculum for solving tasks. So one of them was this paper from some folks at Uber AI that was actually using genetic algorithms and evolutionary methods to generate increasingly complex environments for the agent to learn in. So it was a locomotion-based task where there was this legged robot in simulation that needed to move forward, and then it was generating different different stepping stones and different environments that made it more challenging for the robot to traverse the terrain. And the second one was a single environment, but what it was trying to do, it was essentially trying to play a sort of a kind of a hide and seek game where there were some agents that were trying to hide, and so they were given like 5 seconds or some amount of time to like go hide, and then the seeker agents after that had to go try to find the agents that were hiding. And all this was in simulation, but one of the interesting things was that it kind of learned this sort of curriculum where initially the hiders were doing very obvious things that were pretty easy to find, but then later they would actually start making barricades and making it harder for the seeker agents to actually go and find the hiders.
So the curriculum was, in that latter case, the learning agent was the hider or the finder?
So in this case, actually both the hider and the finder were learned.
Okay.
They were both being learned simultaneously, and the curriculum emerged simply from the fact that this was a multi-agent optimization.
Mm-hmm. And
so basically, as the kind of hiders would learn some sophisticated behaviors, and then they would be winning, and then the seekers or the finders would start to learn more sophisticated behaviors as well to go find them, and then you would have this kind of alternating thing where one of them starts winning, and then the other agents will need to learn more sophisticated behaviors to overcome the types of strategies that the other set of agents learned.
Right. It's probably worth taking a step back and kind of providing a high-level overview of curriculum learning. As I understand it, again, I think you were the first person that explained this to me. The idea is that in any kind of scenario like that, you might have a reinforcement learning agent in. A big part of the problem is that the state space is huge, and that's not unlike how we as humans learn. If we had to learn everything, the possibilities are huge. So in school, for example, we create a curricula that has us learn, X then Y then Z. And in doing so, that kind of creates a more narrow path for us to get through this, the possibilities. And curriculum learning is trying to do something similar, where first you teach the agent to do the first thing, then you teach it to do, like in the case of some of these locomotion examples, you teach it to crawl, then you teach it to stand up, then you teach it to run, then you teach it to jump, that kind of thing.
Yeah, exactly.
Does it count as curriculum learning if it's just something that the agent does without, some special capability to learn curricula? Does that make sense? Particularly around that second example with the hiders and the seekers. What we're doing, we are kind of observing after the fact, the things that these agents did and calling it curriculum learning. But was there something specific to the agent that, made it learn in that way? Or is that kind of orthogonal to the point anyway? Does it not matter?
Yeah. So to me, I think that a curriculum is characterized by an increase in complexity. And if for kind of at the beginning, you learn very simple things, and at the end you're doing much more sophisticated and complex behaviors, then it seems like there's this progression of simple to complex. In the case of the first paper, this was fairly explicit. In the case of the second paper, I think that this was more of an emergent property of the algorithm, or an emergent property of this multi-agent optimization, and it wasn't necessarily something that was built into the algorithm from the start. And I think that just this progression from very simple behaviors to very complex behaviors is the thing that's very exciting to me, because it means that if we can move from very simple behaviors to more complex behaviors, then maybe we can also move from very complex behaviors to even more complex behaviors.
Mm-hmm.
And it seems like a path towards agents that are increasingly sophisticated and increasingly intelligent.
And so from that perspective, it doesn't matter to you whether that's because of a training regime that has curricula built in that we create, or whether it's just something that, this complex that emerges in a complex system.
Yeah, and I actually think that potentially is maybe even more exciting if it emerges, or if the agent creates it itself, because that means that it won't rely on us for moving to the next level.
The next couple of papers were focused on exploration problems.
Yeah, so these are kind of getting back to Atari land, and in terms of the applications that they were studying, and in general, exploration is kind of a huge challenge in reinforcement learning. It's the problem of discovering the right thing to do in settings where you're not given a lot of supervision, oftentimes, about what the right thing to do is. So you basically need to explore your environment and find the parts of your environment, the parts of your state space that give you high reward.
Mm-hmm.
And in the past, one of the kind of classic problems or benchmarks in exploration and reinforcement learning has been this Atari game called Montezumas Revenge. I don't think it's the only problem that we care about in the context of exploration, but it's one that has been notably challenging for our current reinforcement learning systems. And these two papers were both proposed means for actually solving Montezuma's Revenge to a very large degree, scoring tens of thousands of points on this game, when I think previous approaches were often only getting 0 points or just like a few points on the game. So I think that like these approaches were making a lot of progress there, and kind of the key insight of the first one, which is actually a little bit controversial, was to find the parts of the game where you're getting making some progress, and then actually, if you then die at those parts of the game, actually reset to that state and start kind of exploring in that region of the state space again. And so really trying to remember the visited states that are promising, returning to those promising states, and then explore from it. And so one of the reasons why it was controversial is that they were using this reset ability to kind of go to a particular state that you had been to before. And in many real world contexts, that's of course not something that you can do. But if you're an Atari game, that is something that you could conceivably do. And then the second paper took a very similar approach, but they lifted this assumption by using an imitation learning approach to kind of remember how to get back to that state.
So both of these papers are share in common that they take advantage of ways to spend more time exploring difficult areas of Montezuma's Revenge. One using some kind of God mode reset capability, and the other is just remembering how they got to given states and getting there before they start doing exploration.
Exactly. Yeah.
Okay, I can see how the first one is controversial because in the paper they kind of report their scores, but if you keep doing these unnatural things like resetting and going to hard places and kind of accumulating more score, it doesn't seem to be comparable to the other scores that are reported for this game.
Yeah. I think it's just worth briefly mentioning that I focused on a number of, I think, conceptual advances in various approaches, and at the same time, there have been these fairly large efforts to try to use reinforcement learning and other approaches to solve harder types of games. So StarCraft, there's a large team at DeepMind that was trying to solve a version of StarCraft through reinforcement learning and also imitation learning. And there was also a fairly large team at OpenAI that was trying to study reinforcement learning algorithms on the game Dota 2, and both of them made quite notable progress in those settings. And I feel like I can't summarize 2019 without at least making a very brief mention of those two results.
Yeah, and OpenAI on the Dota front has been working on this for a while. This goes back to 2018 at least, potentially earlier than that.
Yeah, and I think that StarCraft actually also goes back into 2018 as well. I think that they've been long efforts.
So one of the other things that we like to cover in these AI Rewind segments is more kind of practical, tangible advances in terms of new tools and libraries and open source projects, things like that. And you had a number that come to mind. Where would you like to start?
Yeah, so let's start with some of the libraries that have been made available. So in general, reinforcement learning, building reinforcement learning algorithms is challenging, and it's still in the stage where for deep reinforcement learning algorithms, many algorithms can be, first there's just so many design decisions when designing a reinforcement learning agent, such as when do you collect data, how do you collect data, do you collect data in like at a per time step level versus like at an episodic level? Do you normalize your states and actions? Do you How do you kind of estimate your return? There's just all of these really tiny design decisions that can actually make a pretty large difference on the result of the algorithm. And so having implementations of reinforcement learning algorithms that are trustworthy and are actually kind of ready to use out of the box for different applications, I think is quite important for the advancement of reinforcement learning. For kind of specific algorithms, there have been a number of open source implementations released by the authors of those papers, and in many times those implementations are in some ways the most trustworthy because they're the ones that should reproduce the results in the paper. But there's also been a library called TF agents or TensorFlow agents that provides actually a platform of many different algorithms, many different reinforcement learning algorithms, and is trying to basically provide a kind of a unified code interface and framework for running these different types of algorithms, and making it with the goal of making it easier for people to use these algorithms on their problems.
And so, how much of the problem of getting an RL agent up and running does TF agent solve? Does it get you all the way there? It's always struck me with RL, there are just so many moving pieces. You've got your simulation environment, or your game environment. You've got your agents. You've got to figure out your optimization, your loss function. How much of that does TF agents take care of for you?
So if you want to use an environment like OpenAI Gym, for example, then I think that you should be able to run it like it basically will solve everything for you. If your environment interface is different from Gym, then of course you'll need to do some plumbing essentially to hook it up with that. And it also doesn't solve the fact that if you have a new environment, these algorithms may not work out of the box on that environment because of you may need to tune it, or maybe just that your problem is harder than the current kinds of reinforcement learning problems that we can solve.
Mm-hmm. But if you want to reproduce one of the standard algorithms using a known environment like Gym, you should be able to do it fairly handily.
I think you should be able to do it fairly handily with this code base. It's also worth mentioning, I think that this is from very late 2018, but there was also a framework called Dopamine that was trying to do something somewhat similar, but they had a more narrow focus, which was to study Q-learning algorithms, various types of Q-learning algorithms for Atari games. So things like deep Q networks, distributional reinforcement learning, prioritized experience replay, all the bells and whistles that you might want in your DQN agent, specifically looking at Atari games. That code base, I think, provided a very reliable implementation of that kind of suite of algorithms, which basically with a more narrow focus than TF agents.
And you also mentioned PyTorch Higher. What's that all about?
Yeah, so this isn't necessarily a reinforcement learning thing, but it's a library that's been very useful for meta-learning research. So I don't know how much of the details I want to get into with meta-learning, but kind of the goal is to learn, as I kind of mentioned at the beginning, the goal is to learn priors from previous experience in a way that allows you to learn very quickly, like learn with only a few data points for new tasks. And one very popular approach for meta-learning is to perform what's called a bilevel optimization, where you're actually embedding an optimization process inside another optimization process. And Higher provides a way to perform these higher order optimizations. Like, for example, if you're embedding one optimization inside another, you have a second order optimization process. And this library makes it very easy for people to do that. And I haven't used it personally myself, but my PhD students have been using it and have said wonderful things about it.
Is the idea with bilevel optimization and meta-learning that you're optimizing whatever problem you're trying to solve at one level, and at another level you're optimizing the way you learn how to solve that problem?
Exactly. Yeah, that's a great way to put it.
And so Higher isn't necessarily a meta-learning library, but it's a general bilevel optimization library, or is it more specifically geared towards meta-learning?
It is a more general thing, but they also provide a number of optimizers that make it good specifically for meta-learning use cases.
Okay. And maybe to further kind of, skirt this line of going too deep in on meta-learning, is there a classic problem setup or hello world of meta learning that would help make it more concrete for folks that aren't familiar with it?
That's a good question. Yeah, so I think that maybe one very simple, like one kind of very standard problem in meta learning is, can you learn to recognize characters of a new alphabet with a few examples? So can you, given like, I don't know, an example of 5 different handwritten digits, can you learn a classifier that can distinguish those 5 handwritten digits? And the way that these meta learning algorithms work is that they take handwritten digits from a number of different alphabets and languages and learn at the lower level. They're trying to learn how to distinguish digits from a particular alphabet, and at the higher level they're trying to change the way that lower level learns across alphabets in a way that makes it generalize faster, and in a way that makes it allow it to learn from only 5 examples. So for example, if you trained a deep neural network on 5 examples, it would probably overfit massively or not be able to learn very much. And these algorithms try to actually train for the ability to generalize from a few examples by changing the way that neural networks are learning.
So we've talked a little bit about OpenAI Gym and some of these other simulation environments. There were also some new ones that were introduced this year.
Absolutely. So, and I think that kind of maybe jumping ahead a little bit too much is one of my predictions for next year is that we're going to really need better environments for studying the kinds of problems that we care about. So I think that if we care about things like generalization, like the ability to learn new tasks quickly, like the ability to solve longer horizon tasks, maybe with the use of demonstration data, then we need environments that allow us to actually evaluate those abilities in our algorithms. And there have been a number of environments that were introduced this year that tried to focus on different aspects of this. So, for example, there was the AI Habitat environment that was developed specifically for visual navigation. And it was specifically trying to target the setting where you want to learn how to navigate environments with photorealistic rendering, where basically you're dealing with images where your observations are highly realistic images, such that you aren't learning from these kind of really simple game graphics. So it's such that you're actually studying both the vision aspect of the problem as well as the control aspect. The second environment is the meta world environment, which is an environment that one of my PhD students and some of my collaborators have been working on, where we've been trying to study or allow ourselves to study generalization across tasks. So we create a benchmark of 50 manipulation tasks in simulation, and with the hope of seeing if it can allow us to study, 1, whether or not we can have algorithms learn across all of the tasks, and 2, whether or not we have algorithms that can use, say, 45 of the tasks in a way that allows you to quickly learn new tasks, like the next 5 tasks. And that was kind of targeting meta reinforcement learning algorithms that can learn how to learn from small amounts of data or small amounts of data for new tasks. The MineRL competition that I also mentioned has been looking at Minecraft environments, which I think is a really interesting test bed for reinforcement learning methods because it's more open-ended. And they specifically, one of the things that they've been focusing on there was the ability to learn from example behavior and from demonstrations. And so they collected a very large data set of humans playing in these Minecraft environments with the hope of building reinforcement learning agents that can use this data as well as their own data that they collected themselves in the environment in order to learn complex and long horizon skills. The Rexim that I mentioned is a kind of a simulation platform for studying whether or not you can learn a recommender system. And I think that one of the things that I really like about this is that it actually allows you to study a more real world problem that's quite different from things like games and things like robotics.
Yeah, I was not expecting recommender systems to come up here.
Yeah, and I think that people, like, in many ways, the reinforcement learning community has been so focused on control, robotics, and video games.
Mm-hmm.
And I think that maybe we're overfitting to some of the challenges in those domains. And if we care about building reinforcement learning algorithms that are useful in a variety of settings, then we should be testing them on things like recommender systems.
Mm-hmm.
And I hope to see more of that too. Like, you can imagine education, as I mentioned before, medical decision making. I think that there are a lot of potential applications of reinforcement learning where sequential decision making, where you need to really reason about the effect of your actions on future states.
Yeah.
And then the last thing is this Google Research football environment. And this one, I believe, is specifically focusing on the ability to study multi-agent reinforcement learning.
Mm-hmm.
In the context, and by football, for those of us that are Americans, they're referring to soccer.
Yeah, and actually, I did an interview with one of the principals in this work not too long ago. Actually, this is relatively recent, but it was episode 293 of the show, and it was with Olivier Bakken.
Yeah, so those were all the environments that I've seen come up that look quite promising and really filling a gap that I think don't have in our current environments.
Well, you started kind of foreshadowing into your predictions there. One of them being that we need to see even more of these types of environments. What are some of the other things that you expect to see in the field in the next year? And I guess we're going into 2020, so we could even talk about the next decade if you dare.
Yeah, so I think that in addition to an increase in environments that will hopefully allow us to meaningfully study things like generalization and batch-off policy RL instead of repurposing old environments for those things. Mm-hmm. I think we'll also start to see an increase in papers that study settings like batch-off policy reinforcement learning. So I think that this year we saw a pretty big increase in people that are studying that. And I think that that's probably going to continue because that's really a problem that matters in the context of the real world deployment of reinforcement learning systems.
So greater focus on batch-off policy RL.
Yeah, and then I also think that we didn't quite, this is kind of one of the papers that I was going to mention on meta reinforcement learning and multitask reinforcement learning, which we didn't quite get to cover in 2019. And I think that we're also really going to see an increase in papers that study this. So I think that in general, the community has been fairly focused on like trying to solve individual tasks. And that's, I think in some ways that's actually been by nature of the environments. They're focusing on, let's learn one Atari game. Let's learn to run with this one agent in this one environment. And I think that a lot of people really do care about generalization. And we did actually see an increase in papers this year that were focusing on generalization to some degree. And I think that we'll see actually kind of the breadth of generalization that we try to study increase. And in particular, trying to study generalization across tasks, across goals, across objectives, such that we can move towards general purpose reinforcement learning agents rather than these very narrow and specialized agents.
And do you have a sense for what that will likely look like? Is it analogous to what you were doing with the collaboration across institutions and in the off-policy work where you were looking at multiple different robotic platforms and trying to train on different environments simultaneously? Or is it some new training technique or something that results in greater generalization?
Yeah, so I think that I would love for everyone to start studying robotics, but I think that in practice, people won't be people are a little bit scared of robots, and not scared in terms of them being dangerous, but just scared of the effort that goes into actually getting things working on a real robot in the real world. Mm-hmm. And so I think that in practice, what that will mean is that people will be studying simulation agents, like simulated control agents, simulated robots, maybe simulate different like video game levels, for example, and studying how agents can learn across, can generalize across these video game levels, that can generalize across reward functions of a robot, for example. And I think that basically the algorithms are mostly ready for this. I think that there's still advances to be had on just in terms of the ability for kind of just basic reinforcement learning algorithms to be stable, to work well with images, etc. But I think that many of the algorithms are ready to take the jump towards these more complex settings where you need to be doing multiple things and not just one thing. And maybe actually, I mentioned multitask RL, like the ability to do these different tasks, but it could also be doing tasks in sequence, or kind of hierarchical reinforcement learning where you're performing like picking up an object and then placing it into a bin and then taking that bin and putting it somewhere else. Mm-hmm. And I think that in general, people have been studying some of these problems for a long time, but I think that we'll actually start to see meaningful advances in these problems in the deep RL setting and in more complex and challenging environments.
Any other predictions?
I think that the batch-off policy, multitask RL, and meta RL in environments are my main ones. I guess we also talked a fair bit about model-based and model-free. I think that people will continue to show interest in model-based methods, and we'll also continue to see a number of hybrid methods that combine elements of model-based and model-free algorithms as well. Mm-hmm. Yeah, so I think that kind of the things that are going up will continue to actually maybe become increasingly more popular. Things like batch off policy, model-based RL, and meta reinforcement learning and multitask reinforcement learning.
Mm-hmm.
And one of the things that I guess I'm really excited about is that I think people will actually really start to meaningfully study generalization, and I think that this is something that's been overlooked for a very long time in reinforcement learning.
One of the questions that I get all the time about reinforcement learning, and particularly deep reinforcement learning, is, who's using it and for what? Have you come across any notable kind of real world use cases for deep RL this year?
Yeah, that's a really good question. I think that in general, people aren't using it because these algorithms they work in some contexts, but they are still a long ways away from being just like a plug and play thing. Like deep learning, for example, with neural networks, we like with BatchStorm and all the and like ResNets and stuff like that, we really figured out a way to kind of really be able to deploy these deep neural networks in a wide range of settings if you have enough data and can actually formulate your problem as a supervised learning problem. In reinforcement learning, I don't think that we're quite at that stage yet. And there have been some applications. So I know that there are some folks that use it actually for recommender systems. So like Craig Boutilier, for example, at Google is someone who's been studying reinforcement learning in these sorts of settings. There was also one example, I think, a couple of years ago of using reinforcement learning for like data center power management. But I haven't really seen that really expand. Yeah, at least from what I've seen. I think it's also hard to say because it's not necessarily people aren't always public about the sorts of things that the sorts of algorithms they're using in industrial applications. But my guess is that they really aren't being used much in real world applications.
One of the things that makes this particular question challenging is you'll see a lot of people talking about using reinforcement learning, but when you go under the covers, it's not deep reinforcement learning. It's like single step kind of traditional reinforcement learning, which is different.
Yeah. I guess one other thing worth mentioning is that there's a startup company led by Peter Biel and others that is looking at robotic automation, and they're looking at deep imitation learning and deep reinforcement learning for doing this.
That's covariance?
Covariant, yeah. But I also don't know. They aren't very public about the kinds of techniques that they're using or the applications.
I recently saw the Mark Hammond, who has been on this show. He founded a company called Bonsai that was acquired by Microsoft. They're still doing interesting stuff with RL. Like, I think it is happening, but in terms of, to your point, kind of public, detailed case studies about what folks are doing, they are difficult to come by.
Yeah, and like Osaro is another startup company that is looking at deep reinforcement learning, but they, I don't know, if they're actually using it for the use cases or not. And there's also, I guess, another kind of maybe more real world example is that but not deep, is that there was some work, I think a couple years ago by Joël Penou looking at reinforcement learning for brain stimulation for seizures to try to stimulate the brain in a pattern that used less stimulation than kind of the standard thing, while also still preventing seizures. But that was by no means using deep reinforcement learning. It was just using reinforcement learning with smaller models because they didn't have enough data in order to deploy these techniques with deep networks.
Cool. Anything else we should keep our eyes peeled for in 2020?
I think that's it. I'm excited to see what's to come, and I think that I guess maybe one other thing worth mentioning is that there's been increasingly other research labs that have really been entering the reinforcement learning space, and it's been exciting to see that people are getting more interested in the problem setting. Labs that were traditionally doing things like supervised learning and unsupervised learning, and I guess I mentioned this also at the beginning of the podcast.
Mm-hmm. Any particular ones that folks should be keeping an eye on? I mean, there are the, DeepMind, OpenAI, or, traditional folks that have been publishing a lot in this space. Certainly yourself and Sergey Levine and Peter Biel and many others, academic labs. Who are some of the new ones that might be worth taking a look at?
Yeah, so in addition to the folks that you mentioned, some of the kind of existing ones are like the Google Brain team, in addition to
Of course.
DeepMind, of course, and folk labs at McGill in Montreal like Doina Prekup and Joel Panu, folks at Oxford like Shimon Whiteson, and then also folks at Michigan like Satinder Singh and Hung-Lok Lee. And then also at Stanford is also Emma Brunskill. And I think that these folks study different aspects of the problem. For example, Emma has been looking at applications like education and really kind of human impact settings, and really actually focusing on like off-policy methods, for example, while Satinder's group and Hung-Lok's group are often looking at more video game applications. And Joel has done kind of at McGill has done a variety of different applications. So I think that it's been interesting to see how different methods are using different approaches. And then in terms of newer labs, I think that it's hard to list them, but I think that some maybe people who are probably rather recognizable in the deep learning community and that are starting to do more reinforcement learning are folks like Yoshua Bengio and Jan LeCun. Jan more on the model-based reinforcement learning side of things, and Yoshua I think has been looking at representation learning in the context of embodied agents. And then also folks like Jimmy Baugh, for example, has had some interesting work in model-based reinforcement learning recently. And then also Teng-Yu Ma at Stanford has Jimmy is at University of Toronto, and then Teng-Yu Ma at Stanford has done a lot of really great work on theoretical deep learning and has been starting to move in towards the kind of looking at the theoretical aspects of deep reinforcement learning.
Well, Chelsea, that was a ton of stuff to cover. Thanks so much for doing this show, for helping us get caught up on RL and giving us a peek into what's coming next.
Yeah, absolutely. My pleasure.
All right, everyone, that's our show for today. For more information on today's guest or for links to any of the materials mentioned, check out twimlai.com/rewind19. Be sure to leave us a 5-star rating and a glowing review after you hit that subscribe button on your favorite podcast catcher. Thanks so much for listening, and catch you next time.